I was going to ask, do we have to get on your schooling page?
Yeah, I can give you the code. Well, no, it's the same one. Everybody's in the same one. Okay. So, obviously a little different. I'm different than Grassy and different than Budden, but we do record the lessons whenever I remember to do that. Those are available online, and I'm sure coming from Grassy and Budden, you've had access to them also, so if you need to refer to those. We're just going to pick up where we left off, which is talking about logarithmic, exponential, and other transcendental functions. This will be fun. Natural log, ln, yes? Did a bunch of it in pre-calculus, did a bunch of it, I think, advanced algebra also? Yeah. We're going to take the derivative of that eventually. But the interesting thing that we're going to do today is, the property is, and we're going to talk about E. That'll be good. Yeah, anybody know what E is? Do you know where it comes from?
It's in nature.
It's in.
It is, isn't it?
Fibonacci?
Probably somewhere.
Everywhere. That's what it stands for. E for everything.
E for everywhere.
Everything.
And then we're going to take the derivative of the natural log function. Okay, so let's start with a little refresher. It's been 2 weeks since you've taken an integral. No FN int on this yet. Do this by hand. Solve that problem, please. So you got to remember all the rules. Make sure you're taking an integral, not a derivative. Write it as x to the negative first. Blah, 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 blah. Get those synapses firing again.
It's been a while. So.
Maybe before I give you that, we should review.
That's a good idea.
How do you take an integral?
1 over 1 plus and then
So is it?
isn't it like 1 over and then the number
Be
plus
specific.
1?
So
Oh, so it'd be like 1 over 2 plus 1? No,
yes, 1 over 2 plus 1, which is
1/3.
good.
And then I can't remember if it's you add 1 or you subtract 1.
Do we add 1 or subtract 1?
Add one.
You add 1, right?
Yeah.
Okay. Add 1 and multiply by the reciprocal of that number. So x to the 7th would be 1/8 x to the 8th. Thank you, plus c. Good job. Okay. Now do that. That should help. Those of you that were on the struggle bus.
No, I like this better. Don't worry about it.
Okay, so what's all the buzz about? What's that, Kev? So what's x to the 0? 1. Is that a problem?
No.
But there is a problem in there, right?
And then they give you the values, you plug in 4 and 1, right?
No, well, you missed a component to that.
No, because it's 1 over.
Well, we will eventually. Yeah, we're getting to that. Yeah, that's where this is getting us to.
What?
Yeah.
No.
Okay, so what's the rule again? Yeah, let me do this, and we'll get some blue action going on. Hopefully this is working. Integral from 4 to 1 of x to the negative 1 dx. Okay, what's the rule we just practiced over there? Add 1, so negative 1 plus 1 is 0. Multiply by the reciprocal of that.
Whoa.
Is this a problem? No, that's 1. Is this a problem? You bet it is. Okay, so now what do? What's the answer? You want to go with undefined. You can't BS your way through that 1 over 0?
Yeah, John can.
Make it 0? Well, what have we learned about anything over 0? It's always undefined. Okay, so I can just start shouting out calculus terms. Implicit differentiation.
Take a limit.
Okay, I can accept that. Can we all accept that? It doesn't work. Right? That's going to be a problem, though. How do we define an integral? Sorry, how do we define a definite integral? Yeah?
The area under the curve.
Area under the curve. Do you know what that looks like?
Yeah.
Will it have an area under the curve?
No.
It won't? Well, that's a dot. Hold
At
on.
certain points it won't. Like,
There's the graph.
but then it's open at 0. You know what I'm saying?
Look at the limits of integration.
1 to 4.
If we've done this correctly, or if we could do this correctly, 2, 3, 4, what we should get is a number that represents this area. Is there an area there? Is that area defined? Yeah. So why, from a geometric standpoint, it should work. We should be able to get a numerical value. Will that numerical value be positive or negative?
Positive.
Positive. Good. But according to the calculus, it doesn't work. Question?
Is it because there's an asymptote at 0?
Has nothing to do with 0. Because notice I'm not going over that far. If I asked the original problem going from 0 to 4, then we'd have a valid argument that it just doesn't work.
Yeah.
Because that area is increasing without bound is the fancy term.
It's just infinite.
Right. Go ahead.
Isn't it because when you do the whole integral and you do the whole process, you're not doing it for your domain, you're just doing it for the general graph. So for this general graph, the general graph doesn't have a domain from 1 to 4, it has it from infinity to infinity.
That's not a horrible statement.
Yeah.
Right.
So you need another tool. You need another strategy.
Oh, I couldn't have said it better myself. So we need a different strategy.
Yeah.
So what we did is we invented a strategy. Be nice if I could work my own pen. That strategy is natural log. That's where the natural log comes from. So now you never learned this. You just learned the natural log is log base e. Right? Yes or no?
Yeah.
Yeah. And then when you said, well, what's this e thing? Your teacher told you it's 2.7, blah, 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 blah. But never explained where e came from. So you have this little sprinkling of mathematical fairy dust that says, oh, we're just going to pretend and do this. Well, now from calculus, we can't accept that. Natural log is defined as the area under the curve of that particular function. Since we cannot do the calculus to find that area, then, as Dee Dee said, we we cheat. And we make our own tool to be able to do that. And that's where the natural log comes from. And notice the natural log starts at 1. So it's the area under the curve of 1 over x from 1 to whatever value it is. As the number gets bigger, the natural log gets bigger. As the number gets smaller, the natural log gets smaller. Question?
Yeah, I'm just a little confused with the fact that it's the natural log of x, but then you're taking the, for the antiderivative, it's talked about t.
That's a variable change. Yeah,
So where does the 2.7 come from?
patience. We'll get there. That's a great question. Calculus will explain that. We could have called this whatever we wanted to. Why did we call it a natural log? Well, because we're cheating. We actually, I know where we're going to, but I mean, you could have called this function whatever you want. So it's a natural log. And it's defined as the area under that curve that I just showed you. That's it. It's just a definition. Are we good? Okay. There's a graph of the natural log function. You've seen that before. Passes through the point 1, 0. Domain restriction, range restriction. It's continuous and it's increasing. And it's concave down. So now we incorporate a bunch of calculus terms into that natural log, which you've seen before from pre-calc and even probably advanced algebra. Okay. Can somebody please explain to me why that equals 0? Why does the graph pass through the point 1, 0?
Should be 1, 1.
Why would it be 1, 1?
This is 1 over x.
That's true. But how is the natural log defined?
As, oh, the antiderivative of 1 over x.
Correct?
So, at the point 1, the antiderivative would be, or,
It's 1 over 1 times x to the 0.
So we define the natural log of x as being the integral from 1 to
1 to 1.
X
doesn't go anywhere.
of 1 over, let's make it simple.
oh, good
Yeah.
stuff, Johnny, there's no area there.
There's no area there. What about this region?
Negligent, starts at 1.
Yes.
Why is it negative though? Why does it go below the x-axis? Let's say, for instance, at 0.5.
Oh, because you
Oh,
go back.
Why would it have it? Yeah.
From 0, or from 1 to 0, you go back.
We would have the integral from 1 to 1/2 of 1 over x dx. And when the upper limit of integration is smaller, you flip them and put a minus sign on front. So this would be the same thing as the opposite of the integral from 1/2 to 1 of 1 over x dx. Okay, good. Question?
Why does one of the properties say that it has to be concave downward? Like, why can't it be concave up?
Can you wait?
I guess.
Because when we start taking the derivatives, you'll see why it's concave down.
Okay.
Because when we learn how to take the derivative of the natural log, then we can take the second derivative and see that it's always going to be positive or negative. It's concave down, positive or negative?
Negative.
It's negative. Okay, good.
Oh my.
Pre-calc stuff. Yes? We talked about that already. The natural log of 1 is 0. If you have the natural log of a product, it's the natural log of a product is the sum of the natural logs. With the exponent, you can move it out in front, and a quotient becomes a subtraction problem. Those are the log properties that you did last year or in advanced algebra, and you hated them, and you forgot about them, and now they come back to bite you in the keister. So for instance, the natural log of 3x would be the natural log of 3 plus the natural log of x. Which is also a little weird because everything we've done up to this point has been the derivative of a sum is the sum of the derivatives. The product, blah, 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 everything's matching up. Now we change it. Product becomes sum, division becomes subtraction. Okay, we good? Let me just flash all these up here because we probably don't need to talk about all of them, but we can see how you can break these things down. Starting with a complicated, the reason I showed you both is because you're going to have to be able to work with both. Take a single natural log and break it into components of natural logs, or take a series of natural logs and bring it back together into one natural log. So be able to go from left to right and from right to left. Question in the back.
For B, can you split apart the 3x also? Just in a...
No.
No, because it's in...
The natural log of a sum doesn't break into
Oh, okay.
anything. Yeah, only the natural log of a product or the natural log of a difference. These are as simple as they get. And again, this isn't earth-shatteringly important, but we will use it, and knowing these will make your life a little bit easier when we start taking derivatives. Okay, let's talk about E. What'd you say E was, Sam?
2.71.
That's it? That's all you got?
Yeah.
Okay. I'm going to show you a trick how to remember E out to, I think, 10 decimal places. But it involves a $20 bill.
Oh yeah, Mr. Troy showed us that.
Somebody have a $20 bill?
That's why he's gone. That's why he's gone.
Doesn't seem like smart to
He's
give you
still
a $20
someone.
bill.
Well, I'm not going to run out of the room.
I don't know.
Who's on the $20 bill?
Jackson.
Okay, well, hold on a second.
Oh,
That's a $20 bill,
right?
right?
Didn't do a triangle.
Who's on the $20 bill?
Andrew Jackson.
It says Jackson down at the bottom, right? It's a dead giveaway. What president was he, Sam?
The mean one.
Oh. 16.
No,
that's it.
Quiet!
Oh
Nope.
my.
Sam, you know?
No.
7.
Oh, I think it's really
Sam, do you know what year he was elected?
1828.
Beautiful. He was elected in 1828. Sam, did you know that he ran for 2 terms?
Yeah.
Yeah, 1828.
Wow.
Okay. Shh. Do you also know if you take a $20 bill?
Ripping in half.
Yeah. And fold it,
Paper.
you can make a football. Man, origami skills going on here.
Oh, gee, Mr. Troy. Lexi, were you there? That came. Honestly.
What is that?
Triangle.
What kind of triangle? Shh.
Isosceles.
What?
Isosceles?
Don't listen to him.
I don't know.
What else is it known as? How big is that angle?
Right angle?
90.
Yeah.
How big is that angle?
45.
How big is that angle?
45.
So this is what kind of triangle?
I don't know. Right triangle? What?
You don't remember what those are called?
No.
It's a 45, 45, 90.
Oh.
Or a 45, 90, 45. Thank you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I was wrong. 15? 15 or 16 decimal places?
Just whip that on the AP test.
Don't you memorize it?
Automatic 5.
You just gotta turn the page. There's gonna be a picture of a $20 bill in the last.
Tape it on.
How big is it?
Yeah, tape it on.
That probably wouldn't hurt either. The big question is, however, where does this number E come from?
Andrew Jackson.
Correct. Andrew Jackson invented the number E. How strange is that? He put this together. He's like, well, let's see. I'd like to be on the $20 bill. I am the 7th president.
What's gonna happen when he's no longer on the $20 bill?
He will be forever.
It's
No, it's changing, right? Is it the 20 that's changed?
yeah, because of Hamilton. So they aren't changing.
Because of the
percent-
play Hamilton, he
I
gets bumped
think
off the $20 bill?
I think
What is the
so.
play?
Native Americans hate it.
They're keeping Hamilton.
Because Hamilton was such like a
I'm sorry, what?
The Swiss guy.
Yeah, Harry Tubman.
yeah Terry Tubman.
Yeah, Harry Tubman. Yeah, but it had, what does that have to do with Hamilton?
So like it was gonna be the $10 bill, which is Alexander Hamilton, but because of like Hamilton the musical, and because
Shut
of,
up, are you serious?
that's what I read in an
I find that
as-
hard to believe.
Yeah,
How
because
does
the
Ulysses S. Grant deserve to be on the 50? That's all I know. What did he do besides win the Civil War?
And we tried
Yeah, that little thing. All right, so here's where E comes from.
46.
We go back to our definition of the natural log, and this is the reverse of what you learned about in pre-calc. In pre-calc, you learned about E and then said, okay, now let's make that the base of a log. This is doing the calculus approach, defining the natural log first and then telling you where E comes from. E is that number that I come out to so that the area of that little pink region is equal to 1. Okay. So we're putting the cart before the horse here. In other words, it's a little hard to see in my graphic here, but it's saying that from 1 to E of 1 over x dx, that's going to equal 1. So how far do I have to come over here so that this area has an area of 1? And the answer is this number E.
Why do we want 1?
Because we can.
That's a really good question.
Like, what's so special?
Why 1? Why not 5?
Yeah.
Why not 10? I don't know. I really don't. I don't know why they chose 1.
There's one. There's a Swiss guy.
So you keep bringing up the Swiss. What is with you?
I'm just saying. Give him some
What's
credit.
Swiss guy.
I think he was Swiss. Maybe he was German. Oh, the guy who discovered E.
Andrew Jackson.
No,
He's a
no,
Swiss. He's American. Who
He's
discovered
a
E?
common man.
I think it starts with an L.
I'm on it.
Oh, I
I'm
don't
on
think
it
he's
first.
German.
Leibniz, you're talking about?
Yeah. No, I think Leibniz is German.
Oh.
Look that up, will you?
Who discovered E?
Huh?
Who discovered E? Was that
Oh,
that guy?
It might be a German guy.
Leonard Euler.
Oh, Euler discovered E.
Euler.
Is he Swiss?
He's not Swiss, though, is he?
No.
Bavarian?
Can we do an Euler line refresher?
No.
Switzerland definitely played a role in it.
You think so? Somewhere along the line.
Yeah.
Maybe Euler wore Swiss watch.
Yeah, could be.
He calculated it to 23 decimal places.
So where's he from?
He's working on it.
He was.
Oh, I told you.
That's why it's an E though, it's Euler's number.
Now, did you just pull that out of your butt, or where did
I
that come from?
the sobriety taught me that.
Oh, okay.
Oh.
Taught you about the Swiss.
Guess, if you're gonna guess math,
you're gonna guess a Newton, Euler,
It's like a party trick.
or
Like, you
Leibniz.
don't
So I mean, that's pretty solid.
All right, and again, going back to pre-calculus, what you learned is, not Euler, what you all learned is that when you take the log of a base of that number, you get 1. So if I take log base 2 of 2, I get 1. If I take log base 7 of 7, I get 1. Same thing as here. Log base E of E will give you 1. But now, again, we come about it from a different approach here. Now we're using calculus to explain that. You didn't really explain it in pre-calculus, you just did it. I mean, you talked about log properties, and then all of a sudden you said, okay, let's take this magical number and put it in as the base, and look at all these cool things that happen. For us, however, now we can explain it using calculus. And again, there's a calculation-based component of this. What happens when I take the natural log of E? Well, the calculation part is here, but there's also a graphical part to remember that this thing represents the area under that curve such that the area is equal to a value of 1. And again, I don't know why it's 1, but it looks good. Okay. Check these on your calculator. This does not matter about the mode, but you should get the same numbers there.
Why is it negative?
I was going to ask you the same question, Kev.
Let's go backwards.
So this kind of just to make sure our calculators work.
Yep.
There it is.
Wait, I was thinking it too, because if you like do like the quotient one, and like A is bigger than B, you get, or like, yeah, or like B is bigger than A, you get like a negative. Ow.
Because we've defined an integral going from left to right. Yeah.
Oh no, we were just talking like, what if you plug one of those in your calculator? It's like, nice try.
So we defined an integral as going from left to right. So we go from 1 to 2, we're going from 1 to the right to 2. But what happens when we go to point 1? We're going from 1 backwards. And so when you go to the left, you have to switch it and put a negative sign in front. Okay, that's the calculation part of it. The graphical part of it is the graph is below the x-axis. Okay. The one thing that's up here is take the natural log of -5.
It's not non-real.
Error.
You should take it to a raise.
I thought you could reset on the back, like,
It's just not
I
real.
think it's probably out of battery. Is it charged?
I charged it like 2 weeks straight, and then it worked for the finals.
You know what time it is? I would take it home and try and charge it tonight and see if that fixes it.
I had the same thing happen with mine. I
Yes.
didn't get it anyway.
Wait, hold on. You haven't answered my question. What happens when you take the natural log of a negative number?
It doesn't exist.
They're not real.
It's not a real number.
The Taylor the Prophet is so many problems. It's Taylor the Prophet.
The calculator is when it's learning.
Oh. See that little eye at the end of it? You don't want that. You don't want to do it. So I went to the mode. Okay, this applies for everybody. Hit the mode button, please. And then down at second from the bottom, you'll see where it says real, a plus bi, re raised to the theta I. Make sure real is selected. We only deal with real numbers in here. What you couldn't see is the i's
Keep it
around the
real.
end there. So now if you go back.
You gotta keep it real.
Ah, there we go. Okay.
Pre-calc, they don't keep it real.
Should get an error.
It's the essence.
Pre-calc is fuzzy math.
Not even the asymptote, it's just out of the domain of the.
Oh,
of
it's
the-
from
Yeah, it doesn't,
1 to 1.
it doesn't work for us. Alright, now we're gonna take the derivative of that beast.
Wait, Mister, couldn't you technically, if you were to do it with calculus, couldn't you take the natural log of -5? Because wouldn't it just go the other direction?
No, because you saw the graph of the -5 and it doesn't,
Oh, it doesn't cross.
it doesn't go, yeah, it doesn't go over. It's not taking the opposite of the natural log of 5,
It's taking.
it's taking the natural log of -5. Okay, this one's pretty easy. Blah, 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 blah. Yeah, how do I get it? It's right there. Okay. The derivative of the natural log, so think about how we define the natural log. The natural log is defined as the integral of 1 over x. So if I take the derivative of the integral, I end up back where I started, and that was what we called this second part of the fundamental theorem of calculus. We had this.
Did you win the lottery?
And we want to know now what happens when you take the derivative with respect to x of this guy, which would be the same thing as taking the derivative with respect to x of that guy. And the fundamental second part of the fundamental theorem of calculus says when you take the derivative of the integral, they cancel each other out, and we get what we call the variable replacement. We end up with 1 over x. Easy peasy. You will not use 1 very often. You'll use 2 more often. U prime over u. The reason we don't use 1 very often is 1 only works in that one particular case. What if it's just natural log of x? That's it. That's never going to happen. I shouldn't say never. That will seldomly, if ever, happen. We're going to be looking at something like this. We'll be taking the natural log of a function.
Not the UD.
Okay. So you take the derivative of the u term, you put it over itself. Okay. U prime over u, over and over again. Okay. So take the derivative of the natural log of 2x. What's u prime? What's u prime?
The derivative of
2x.
Natural log of 2.
Hold on, let's back up. What's u in this problem?
2.
2x. So what's u prime?
2.
2. What's u?
2.
2 over 2x is? 1 over x. Okay. Okay, don't overcomplicate this. Okay, are we good with that? Okay, good. Yeah, all right. What's u?
X squared plus 1.
X squared plus 1. So right away, if you want to slap that in the denominator, you're good to go. What's u prime? 2x. Do not cross out those x's. How are we doing so far?
What?
Oh.
Yeah. Okay, so now I've got a product rule.
Why?
Because it's the derivative of a product. That's the product rule.
Why?
And this could be a little confusing for people because we were doing derivatives, then we stopped derivatives, then we did integrals, and now I'm asking you to come back to derivatives. And so your brain is scattered. Is a product rule work here? Because integrals don't have product rules, but this is a product, so therefore we would have a product rule because we're taking a derivative of that. Okay, but beautiful. First times the derivative of the second, plus the second times the derivative of the first. That's it. Okay. What's this?
The derivative of the first.
Well, I know what it says. What is the value of this? 1 over x. What's the derivative of that? 1. Okay, derivative of x is 1. X times 1 over x is 1. Natural log of x times 1 is natural log of x. We're done. How can we make it more interesting?
Trig.
Chain rule.
Just add trig.
Chain rule would work. Trig. We could put trig inside a chain rule or a chain rule inside a trig.
Let's not do that.
You don't want to?
I don't wanna do that.
To be honest, I don't remember I don't even know if there is a D. But if there is a D, I'm guessing it's probably a quotient rule.
Oh, that's not bad.
But it's so funny.
I mean, I still get confused on what trig functions are a product or a chain
I thought you were
rules.
gonna say which trig functions are trig functions.
No, I know those.
You're good on the sine
yeah,
cosine.
with
Okay,
those,
all right.
yeah.
Ah, there we go. Chain rule.
That's an easy one.
Yeah.
We need to do the hard ones.
Okay, so
Maybe I'll actually learn this.
let's not count your chickens yet, okay? Hold on.
All I'm saying is I got pooched on chain rule. I wasn't here for that today.
Oh.
There was a video.
Yeah, because there's no videos online or
I
PowerPoints.
watched it 3 times. I just could not grasp it.
I understand. And I'm not available for help ever.
Yeah, never.
No,
Not
no,
once.
nope. Nor is Grassy or Bud.
No.
Right.
No.
Or Mr. Will.
Oh, yeah.
Or Mr. Bridie.
Or I could go to Mr. Troyer's house if I really
Oh
wanted.
my
That wouldn't be creepy at all.
Sometimes I see him at the Arlington Heights Library.
Yeah, just get him when he's mowing his lawn.
Yeah.
Uh-huh.
Just fly out to Boston and meet him out there.
Okay, so chain rule. Bring the 3 down, reduce it by 1. Bring the 3 down, reduce it by 1. Chain on the derivative of the stuff inside. What's this equal to? 1 over x.
Do you want us to like leave it in that notation? You want it to be like 3 over x?
Doesn't matter to me.
Okay.
As long as it's equivalent, I'm okay with it.
Okie dokie.
Okay? Don't get bogged down in the minutia. U prime over u. And then, of course, it's going to get a little bit more complicated like this and this. But all this little stuff should be second nature now. You should know how to do a product rule now. You should know how to use the chain rule. Should use. Or know how to. We're going to save this for tomorrow because this is going to make some of you cry. But as it says up here, I've got another tool / weapon for you to use in the process of taking derivatives. And it's called logarithmic differentiation.